Welcome to The Explainer. Today, we're going to talk about something you probably never even think about: rubber. I mean, it seems so simple, right? It's bouncy, it's stretchy. What more is there to say? Well, it turns out there's a whole world of hidden physics under the surface. So let's get into it.
So here's the big puzzle. We all know rubber bounces back. You stretch a rubber band, it snaps right back. But it also does this other really weird thing. It can slowly deform, almost like a super thick liquid. How can it be both of those things at once? And maybe more importantly, how can we trust it to hold up something like a massive bridge if it's kind of slowly oozing?
You know, this whole phenomenon actually has a name. It's called stress relaxation. It sounds complicated, but it's not. All it means is you stretch the rubber, that's the constant strain, and you just hold it there. And what you'll find is that the force, the stress inside the material, actually goes down over time. It just relaxes. And understanding this is absolutely crucial for engineers building, well, pretty much everything.
To really get to the bottom of this, we have to ask a really basic question. Is rubber a solid or is it a liquid? Turns out the answer is kind of both. It just doesn't play by the normal rules. Think about it like this. On one hand, you have your perfect solid, right? Like a spring. It stores up energy when you stretch it, and then it bounces back instantly. On the other hand, you've got a thick, viscous fluid like honey. It doesn't bounce, it just flows and slowly deforms. The absolute magic of rubber is that it's doing both of these things at the exact same time.
And this awesome split personality has a fantastic name: viscoelasticity. It's right there in the word. You've got visco for that fluid, honey-like behavior, and elasticity for that solid spring-like bounce. And for engineers trying to map this out, the perfect mental image is a spring for the bounce, connected to a damper, like a dashpot, that provides that slow, gooey resistance.
Okay, so if rubber is basically a collection of springs and dampers, how do you arrange them to actually predict what it's going to do? Well, scientists have come up with a few different ways. For our explainer today, let's treat them like three suspects in a police lineup, each one trying to solve the mystery of stress relaxation. So first up in the lineup is the Maxwell model. This is the most basic, no-frills approach. Just imagine taking one spring and one damper and hooking them up end to end. Simple, elegant, right? But the question is it too simple to capture what's really going on in the real world?
Suspect number 2 is the Zener model. This one's a bit more advanced. It takes that basic Maxwell idea, the spring and damper hooked together, and then it adds a second spring right alongside them. The thinking here is that this extra bit of springiness will give us a much more realistic picture of how rubber behaves.
And our final suspect is the Wiechert model. This one is the heavy hitter. It looks at the other models and says, one spring damper pair, that's not going to cut it. Instead, it lines up a whole team of those Maxwell-style pairs right next to each other. It's way more complex for sure, but maybe that complexity is exactly what we need to finally crack this case. All right, the lineup is complete. We have our three suspects. And now, it is time for the showdown. A recent study did exactly what we want to do. They took real-world data from rubber experiments, and they pitted it against the predictions from each of our three models. Let's see who wins.
And here are the results. The study used something called an R-squared value. You can just think of it as an accuracy score. And wow, the simple Maxwell model, it only scores about a 76%. Not very good. The Zener model jumps way up to 95%. That's pretty great. But then, look at the Wiechert model. Even with just two pairs of springs and dampers, it scores over 98.4%. It's not even a competition. We have a clear winner.
When you look at it on a chart like this, the difference is just staggering. It's not a close race at all. The Maxwell model is kind of left in the dust. The Zener model gets an A, no doubt. But the Wiechert model is playing a completely different game. It's a nearly perfect prediction of what rubber actually does. So we know who won, but the really interesting question is why.
So what is this winning formula? Why is the Wiechert model so much better than the others? It's not just about throwing more parts at the problem. The reason it works so well actually tells us something profound about what's happening deep inside the rubber itself.
So here's the secret. Stress relaxation in rubber isn't just one thing happening at one speed.
Inside that material, you've got millions of tangled molecular chains. Some of them untangle and relax really, really fast. Others take a lot longer. So you have all these different relaxation speeds happening all at once. A simple model like Maxwell can only capture one of those speeds. But the Wiechert model, with its whole team of spring damper pairs, it can capture many different speeds at the same time. Each pair is tuned to a different speed, and when you add them all up, you get a beautiful, complete, and incredibly accurate picture.
And that accuracy, over 98.4%, isn't just an interesting number for a science paper. It means that an engineer can use this model to predict with extreme confidence how a rubber bearing on a bridge is going to behave for decades. That's the difference between a good guess and rock-solid, reliable engineering.
In the end, the scientists who ran this whole comparison said it best. Their conclusion was clear. When it comes to the real world, to demanding applications, the Wiechert model is the one you can count on. It's the one that just works.
So we've kind of solved the mystery of rubber's weird dual personality, but it leaves you with this bigger final thought. We are surrounded by materials. Everything from the foam in our sneakers to the dough for a pizza that have their own strange hidden secrets. If we can unpack the science of rubber, what else is out there just waiting for us to figure it out?